Okay, let's unpack this. We are doing a deep dive today into one of the most surprising and really singular figures in all of 20th century science.
Absolutely.
We're talking about the origin story of the entire universe as we understand it, and the man who was really responsible for framing that story, Georges Lemaître.
Right.
But here's the hook for you, the learner. He wasn't just a world-class theoretical physicist or mathematical genius or this highly respected professor.
No, he was also a decorated World War I veteran and a Catholic priest.
And a Catholic priest. It's an unbelievable combination.
And that duality, I mean, that nexus between rigorous scientific inquiry and this profound faith, that's precisely why this deep dive is so necessary.
Exactly.
Our sources go so much further than the textbook definition of the Big Bang. Our mission here is to synthesize the sheer scope of Lemaitre's intellectual life. We're talking about his challenges to Albert Einstein.
Famously, yes.
His decades of intense work on everything from cosmic rays to pioneering early computing and, the surprising, very clear philosophical line he drew between his science and his theology.
That tension and the way he eventually synthesized those two lives, it's what makes him so compelling. I mean, if you follow this topic, you know the outcome, but the path he took is just extraordinary.
It really is.
The core revelation, the piece that really anchors his legacy, is this. Lemaître was the first person to mathematically connect Einstein's general relativity equations to the observed fact that galaxies are not just floating out there.
Right, they're not static.
They're actively moving away from us.
And it's more than just a connection. It was a theoretical necessity. It came straight from the foundations of physics. He didn't just suggest the universe was dynamic and expanding.
No, he went further.
He proposed that if you run the clock backward, the entire cosmic history must converge on an initial ultra-dense singular point.
And he gave it that beautiful name.
He did. He poetically and very precisely called that state the primeval atom.
And that concept, born out of pure mathematics and theoretical physics in the late 1920s, that is the foundational concept of modern physical cosmology.
It is.
We're giving you a shortcut today to understanding how the Big Bang Theory, the most widely accepted scientific description of the universe's beginning, how it actually got its start, straight from the mind of its visionary creator. So to understand Lemaître the revolutionary, we have to start at the beginning. We have to look at Lemaître, the young Belgian man. He was born in Charleroi in 1894.
Right, and he was the eldest of 4 children. His family background wasn't one of, academic poverty. It was the opposite. It was industrial prosperity.
Right.
His father was a wealthy industrialist.
Which you'd think would set him on a very particular path.
And it did, initially. Yeah. That background of stability in industry, it really influenced his first academic direction.
Yeah.
Lemaître apparently expressed an early interest in a religious vocation.
So the priesthood was on his mind from early on.
It was. But his father very wisely advised him to pursue a practical field first. So in 1911, he enrolled to study mining engineering at the Catholic University of Louvain.
Mining engineering.
I know.
That's about as far as you can get from theoretical cosmology. It's pure applied physics, grounded in geology and mechanics.
Totally. But that whole trajectory was brutally interrupted, as it was for so many of his generation, by the outbreak of World War I in 1914.
And he didn't wait to be drafted.
No. His service in the Belgian army is one of the first real indicators of his extraordinary personality, his absolute dedication to precision. He volunteered immediately.
And he saw real action.
Oh, absolutely.
Yeah.
He participated in some of the most critical actions, including the fierce Battle of the Yser, which was instrumental in halting that initial German advance.
He wasn't just a background figure in the war then. He was right in the thick of it.
He was. But the legendary detail, the one that tells you exactly who Georges Lemaître was, comes when he was transferred from the infantry to the artillery. He's supposed to be learning ballistics, the science of firing shells.
Right, a very mathematical discipline.
Exactly. And this is a fantastic anecdote from the sources. It speaks volumes about his professional future. Lemaître, just a young enlisted man, is attending a training course when he spots something glaringly wrong.
What? In the training?
In the official manual.
Okay.
And he actually gets into serious trouble. His prospects for promotion were basically ruined due to insubordination.
And the reason for this insubordination? Don't tell me.
He pointed out a glaring mathematical error in the official artillery manual to his instructor.
Oh, wow.
He just couldn't allow the mistake to stand, even if it meant torpedoing his own military career.
That is high-stakes rigor, isn't it? It suggests a man for whom mathematical and physical truth was just paramount. even over military hierarchy and his own advancement.
He wouldn't risk bad science leading to poor outcomes. You can see the physicist in him already. But despite that disciplinary issue, he served with distinction until 1918.
And his service was, in fact, highly recognized. He received the Belgian War Cross with bronze palm,
which was a very impressive distinction. The sources note he was one of only 5 rank-and-file troops to receive that particular award directly from King Albert II himself.
So he survives the war, he's decorated, but he's clearly learned this profound lesson, that theory has to be flawless if it's going to succeed in practice.
And this is the pivot. He abandons engineering entirely. He understands that his true passions are in the fundamentals of physics and mathematics. He goes back to Louvain and gets his doctorate in science in 1920.
What's so crucial here is that this scientific pursuit wasn't an isolated trajectory. It ran entirely parallel to his deep spiritual commitment.
Completely parallel. From 1920 to 1923, he attended the seminary for late vocations, preparing for the priesthood.
Just try to imagine the mental landscape of that man. He's attending religious training, preparing for ordination, and yet he's using all his spare time to master the newest, most radical concept of the age.
Albert Einstein's general theory of relativity.
He was actively blending the most profound physical theory with his spiritual training. He was ordained a diocesan priest, becoming Abbé Lemaître in 1923.
And his spiritual life was extremely serious. This wasn't just a casual commitment. He was a member of the Fraternité Sacerdotale des Amis de Jésus and took formal vows of chastity, poverty, and obedience.
And the sources mention a special vow.
Yes, a votum immolationis, which is a vow of complete submission to Christ. This commitment was totally integrated into his identity.
And importantly, this wasn't seen as a barrier to his scientific pursuit by his superiors. They saw his talent.
Oh, they absolutely did. His dedication was recognized and actively supported by Cardinal Désiré Joseph Mercier, who understood the intellectual powerhouse he possessed. Mercier helped secure Lemaître the funding necessary to embark on this transformative global tour of knowledge that would launch his cosmological career.
And this tour itinerary, this sounds like the perfect preparation for the man who would define the modern universe. In 1923 and 1924, he was a research associate in astronomy at Cambridge.
And his mentor there was the towering figure of Sir Arthur Eddington,
who was absolutely central to his development.
Vital. Eddington introduced Lemaître to modern cosmology, stellar astronomy, and, very significantly, the emerging field of numerical analysis.
And that exposure to quantitative methods, to using algorithms to solve problems that can't be solved analytically, that's what sets Lemaître up for his highly practical work later in life with computers and cosmic rays.
Exactly. Then he continues, spending the next year in the United States. He worked at the Harvard College Observatory with Harlow Shapley.
Shapley was the preeminent authority on the mysterious spiral nebulae, which, thanks to him and others, we now understand are separate galaxies outside our own Milky Way.
And he doubled down on his academic standing. He registered for a doctoral program at MIT, getting a second doctorate there in 1927. He wasn't just reading textbooks. He was strategically absorbing every piece of cutting-edge knowledge, every piece of observational data from the absolute global forefront of physics and astronomy.
So by the time he returns to Louvain in 1925 as a lecturer, he's globally networked, he's fully credentialed, and he's uniquely positioned to tackle the biggest question of all, the structure and history of the cosmos. Okay, so Lemaître returns to Louvain in 1925. At this point, the prevailing scientific consensus, which was largely shaped by Albert Einstein, was that the universe was static.
Eternal, unchanging, and fixed in size. That was the picture.
But Lemaître, now armed with general relativity and all this fresh observational data, he was about to completely upend that static dogma.
The theoretical bomb dropped in 1927. Lemaître published a paper in a somewhat obscure journal, the Annales de la Société Scientifique de Bruxelles.
The title is a mouthful. Un univers homogène de masse constante et de rayon croissant.
It's a very dense way of saying a homogeneous universe that is expanding, and that explains why the galaxies are moving away from us.
So this is basically the Big Bang idea, written 4 years before he even coined the term primeval atom. But what was the core mathematical breakthrough in that 1927 paper?
It centers on the Friedmann equations. Now, these equations have been derived a bit earlier by Alexander Friedmann, and they describe how the scale factor of the universe evolves over time.
Right.
Lemaître independently derived them. But here is the critical difference. Friedmann treated them as, interesting mathematical solutions. Lemaître was the first to realize these solutions most correspond to physical reality.
So he established that Einstein's own general theory of relativity, the theory of gravity and space-time, it fundamentally implied a non-static universe.
Exactly. It had to be either expanding or contracting. There was no stable, static solution just built into the math itself, despite Einstein's initial insistence.
Einstein had famously shoehorned a term into his equations to force a static solution.
The cosmological constant, lambda, he put it in precisely for that reason, and later called it his greatest blunder. Lemaître realized that if you just abandon the static assumption, you naturally get a dynamic universe.
But Lemaître didn't stop at the mathematical theory. He immediately looked for observational proof to back this up.
He did. He connected his theoretical prediction to the known astronomical data available at the time, especially the spectral data showing that the extragalactic nebulae were redshifted.
Meaning they were moving away from Earth.
Right. And he proposed a simple relation of proportionality. The farther away a galaxy was, the faster it was receding from us.
This is the revolutionary concept. This defines modern cosmology, but because it was published in a niche Belgian journal, it had almost zero global impact at first.
None. And when Lemaître finally got the chance to present this idea to Albert Einstein himself, the feedback was brutal.
It's one of the most famous rejections in scientific history. In their 1927 meeting, Einstein told Lemaître directly, in French, "Vos calculs sont corrects, mais votre physique est abominable."
Your mathematics holds up, but your physical interpretation is terrible.
It's just astonishing that Einstein, the man who revolutionized space-time, would dismiss a mathematically correct deduction from his own theory as abominable physics. Why was he so philosophically opposed?
It really came down to aesthetics, to a belief in the permanence of the universe. For Einstein, the universe had to be beautiful, eternal, unchanging, a static cosmos.
And Lemaître's expansion suggested a finite history, a beginning in time.
Which Einstein resisted profoundly, even though his own gravitational theory was pointing right toward it.
So Lemaître's seminal work just languished for 2 critical years. Then, in 1929, Edwin Hubble publishes his game-changing paper in the U.S.
And Hubble's work was purely empirical. He was using powerful telescopes at Mount Wilson, gathering extensive high-quality data, and he showed a clear, undeniable correlation. The measured distance to galaxies and their observed recessional velocity were proportional.
Hubble had the much stronger data set, and his paper got widespread attention. It began that slow process of converting the global scientific community.
It did. But here is the critical nuance that often gets simplified in history books, and which we have to clarify for you, the listener.
Right. Hubble found the correlation, the data points.
Yes. But he didn't initially interpret that relationship as expanding universe. He considered other possibilities.
Whereas Lemaître, 2 years earlier, had derived the relationship from general relativity. He showed that expansion wasn't just a possible correlation, it was a theoretical necessity if GR was correct.
Exactly. Hubble provided the observational evidence. Lemaître provided the theoretical explanation and the expansion mechanism. That distinction is paramount.
And this distinction eventually led to the historical correction. Lemaître's 1927 paper was finally translated into English and published in the monthly notices of the Royal Astronomical Society in 1931.
And Arthur Eddington championed the work, recognizing it as a brilliant solution to the long-standing cosmological problems.
Now we come to the famous controversy over the missing constant.
Ah, yes. Lemaître's original 1927 paper included an estimated numerical value for the expansion constant, the rate at which the universe expands, which predated Hubble's famous constant.
But that numerical estimate was missing from the 1931 English translation. For years, people suspected this was some kind of historical injustice or maybe an intentional editorial omission.
Right, that he was robbed of the credit.
It would be tragic, denying him numerical priority for the expansion rate. But the sources clarify a much more complex and frankly admirable truth about Lemaître's character.
That's right. The historical clarification came in 2011. It was discovered that Lemaître himself, when preparing the 1931 English translation, deliberately removed those specific paragraphs detailing his 1927 estimate.
He removed them himself. Why on earth would he do that?
Because Hubble's 1929 results were based on far superior, more abundant data, leading to a much stronger and more accurate quantification of the constant.
Wait, so Lemaître deliberately removed his own claim to numerical priority simply because better data existed. That seems incredibly counterintuitive for a scientist looking for fame or credit.
It just demonstrates the depth of his scientific commitment. He was prioritizing scientific validity, the truth derived from the best available evidence, over his own personal priority claim. He sought accuracy above all else. This action speaks volumes about his intellectual integrity.
Incredible. And his priority in deriving the theoretical link was finally officially recognized decades later.
Yes. In 2018, the International Astronomical Union adopted a formal resolution recommending that the proportionality relationship be known as the Hubble-Lemaître law. It took nearly a century, but the historical record was corrected.
So once Lemaître had proved the universe was expanding, the intellectual journey was far from over. In fact, the math forced him to confront an even bigger question.
Right. If everything is moving apart now, what was the universe expanding from? You have to follow the logic backward.
Right to the edge of time itself.
And that intellectual necessity birthed the truly revolutionary concept in 1931. In March of that year, Lemaître published a brief, very impactful report in the journal Nature.
And in it, he proposed that the universe began from a single initial quantum, a state of unimaginable density and energy.
And he gave this beginning a truly evocative name, the primeval atom.
What's fascinating about that term is how it links the physics of the very small, the quantum, the atom, with the physics of the very large, with cosmology.
Exactly. He was thinking about a quantum origin for the cosmos. I mean, that sounds perfectly normal now, but it was radical then. The idea was that this ultra-dense atom was inherently unstable, and it decayed or fissioned, propelling matter and energy outward in an explosive expansion that continues to this day.
This is the first robust scientific formulation of what we now call the Big Bang Theory.
It is.
And his ideas rapidly propelled him into a kind of scientific celebrity. By 1932, his theory was being introduced to the general public in magazines like Popular Science, with these dramatic headlines.
He was presenting his work on the evolution of the expanding universe before major bodies like the U.S. National Academy of Sciences in the mid-1930s.
And critically, he won over his most famous critic.
Yes. Lemaître and Einstein met several times, but their 1933 meeting at the California Institute of Technology, at Caltech, that marked the decisive victory for Lemaître's dynamic universe.
After Lemaître presented his theory of the primeval atom, the sources report that Einstein stood up, applauded the priest physicist, and declared, "This is the most beautiful and satisfactory explanation of creation to which I have ever listened."
That moment is just iconic. It represents Einstein's full conversion from his belief in a static, eternal cosmos to Lemaître's model of a universe with a definite origin in time. It was a massive psychological and scientific endorsement.
Now, you mentioned a fascinating nuance in the sources regarding that quote. What was the ambiguity?
It's important context. While many interpret the quote as this blanket endorsement of the entire Big Bang Theory, some historical reporting suggests Einstein might have been referring specifically to Lemaître's subsidiary idea that cosmic rays could be high-energy fossils or remnants of that initial primordial decay.
I see.
So even if the praise was narrower, it was still a powerful acknowledgement of the brilliance and the coherence of Lemaître's overall physical approach to cosmic origins.
So the theory had its moment of public triumph, but Lemaître's original name, the primeval atom, didn't stick. The moniker we use today came from an opponent, which is one of the greatest ironies in the history of science.
It really is. The term Big Bang was coined in 1949 by the English astronomer Fred Hoyle during a BBC radio broadcast. And Hoyle was a staunch opponent. He was a leading proponent of the rival steady-state model.
Right, the theory that the universe was eternal, uniform, and unchanging, and that matter was just continuously created to fill the gaps left by expansion.
Exactly. So Hoyle used Big Bang pejoratively. He was trying to mock the dramatic, explosive idea of a universe with a beginning in time.
He meant it as an insult, a way to ridicule the idea.
And the name was so catchy, so memorable, that it instantly permeated the public imagination and eventually scientific discourse. It became the permanent label for Lemaître's theory.
While all this was happening, Lemaître was focused on looking for evidence. As you mentioned, his initial guess for the fossil evidence was cosmic rays. But that wasn't the final answer.
No, the true fossil was predicted in 1948 by the physicists Ralph Alpher, Robert Herman, and Georges Gamow, who were also working within this framework of the expanding universe.
And they predicted a different type of radiation.
A different type, yes. The cosmic microwave background, CMB. They reasoned that if the universe started incredibly hot and dense as it expanded and cooled, there must be a residual heat bath left over from the moment the universe became transparent to light.
A microwave afterglow.
A microwave afterglow, exactly. And the final poignant chapter of Lemaitre's life is tied directly to the discovery of that CMB. He needed that final undeniable experimental proof.
The timing is just heartbreakingly perfect and incredibly powerful.
It is. In 1965, two researchers working for Bell Labs, Arno Penzias and Robert Wilson, they discovered this persistent uniform static or noise in their massive horn antenna. They couldn't explain it. They tried cleaning out pigeon droppings, everything.
And they had stumbled upon the CMB radiation.
The ultimate confirmation of the Big Bang. Yes.
Wow.
The discovery provided the solid experimental support that convinced virtually all remaining skeptical experts.
And Lemaître.
Lemaître, who was frail and ill by then, learned of the discovery from his assistant, Odon Goddard, shortly before his death on June 20, 1966.
So he got to witness his theory's ultimate triumph.
He did, the final validation of his primeval atom hypothesis, almost 35 years after he first published the idea in Nature. It was the ultimate vindication of his scientific vision.
It's easy, given the importance of the Big Bang, to just stop Lemaître's story right there. But the sources show his influence extends far deeper into 20th century physics.
Much deeper.
In fact, Lemaître was a crucial champion for a concept that Einstein considered his biggest mistake, the cosmological constant, represented by the Greek letter lambda.
Lemaître's relationship with lambda is fascinating. He didn't treat it as a patch to force a static solution, which was Einstein's original use. He saw it as an essential element of the universe's evolution.
So when Lemaître and Hubble proved the universe was dynamic, Einstein famously regretted introducing lambda. But Lemaître insisted it should remain in the equations.
He did. And he had compelling reasons on both theoretical and empirical grounds. Theoretically, he believed that if general relativity were to be extended toward a broader framework, maybe incorporating quantum theory, the lambda term would be very much welcomed as a necessary component.
So it represents something real to him.
Yes, the energy density of empty space, what we now call vacuum energy.
And empirically, he used lambda to solve a huge problem in the 1930s, the cosmic age crisis. Can you tell us about that?
Sure. At the time, astronomers realized the universe, based on calculations using the early Hubble-Lemaître expansion rate, seemed younger than some of the observed objects within it.
Like the oldest known stars.
Exactly, and measurements of radionuclide abundances. How can the stars be older than the universe itself?
That's a fundamental contradiction. You can't have that.
Precisely. And Lemaître argued that a positive cosmological constant, this vacuum energy, would induce an accelerating expansion at some point in the universe's history.
So it would speed up over time.
Right, and this period of acceleration would effectively stretch the universe's history, giving it a greater total age and reconciling the ages of the oldest stars with the time inferred for the expansion rate.
So he was proposing that the universe's expansion wasn't just coasting or slowing down due to gravity, but was actually speeding up, accelerating over time, decades before we had the observational proof.
Absolutely. And this is why Lemaître is fundamentally linked to the discovery of dark energy. The Nobel Prize in Physics for 2011 was awarded for establishing the reality of the universe's accelerating expansion using supernovae.
And they credited him.
In the materials supporting that prize, the Royal Swedish Academy of Sciences explicitly credited Lemaître with the foundational idea that such acceleration is driven by vacuum energy. He was nearly 70 years ahead of his time on the greatest mystery in modern cosmology.
It's incredible. His work spans the entire timeline of the cosmos, from the Big Bang start to the current dark energy acceleration. But let's zoom in on his other major scientific contributions, starting with the mystery of cosmic rays.
Right, which ties back to his early fossil hunting speculation. Lemaître's work on cosmic rays, which he did in collaboration with Manuel Sandoval Ferrada, whom he met at MIT, was crucial in defining what these high-energy particles actually are.
At the time, there was a major scientific conflict.
A huge one. Nobel laureate Robert Millikan championed the view that cosmic rays were high-energy photons, bundles of light.
Lemaître and Ferrada disagreed. They argued they were charged particles, so how did they prove this in an era before space probes?
They used the Earth itself as a giant experimental laboratory.
Clever.
They realized that if cosmic rays were composed of charged particles like protons or nuclei, they would be deflected by the Earth's magnetic field. And this deflection would cause the intensity of the cosmic rays reaching the ground to vary depending on one's geographic latitude.
The latitude effect. So the Earth's magnetosphere acts like a filter, protecting the equatorial regions more strongly than the poles.
Exactly. Photons, being chargeless, wouldn't experience this deflection. So if Millikan was right, The intensity should be uniform everywhere. Lemaître and Voirda showed mathematically, and others later confirmed empirically, that the intensity does vary with latitude,
proving definitively that cosmic rays are energetic, charged particles.
and disproving Millikan's hypothesis entirely.
To do this complex work, calculating the trajectories of charged particles moving at near-light speeds through a non-uniform magnetic field, Lemaître had to be a computational pioneer.
He was a genuine revolutionary in applying computational methods to theoretical physics. For his cosmic ray calculations, he had to use cutting-edge technology, MIT's differential analyzer computer, developed by Vannevar Bush.
And this wasn't a digital machine. It was an analog mechanical device.
It was designed to solve complex differential equations. He was solving the trajectories using gears and mechanical integrators, essentially, instead of by hand.
And this commitment to computation continued throughout his career.
It did. He used the mechanical Mercedes Euclid calculator throughout the 1930s for intricate calculations. Later, in the late 1950s, he was responsible for introducing the Burroughs E101 electromechanical computer to the University of Louvain.
That's a powerful legacy in instrumentation, but the sources mention an even more significant mathematical contribution in the realm of computation.
This is monumental. The sources note that Lemaître worked out an independent, early version of the fast Fourier transform, or FFT.
The FFT that was famously developed and published later by Cooley and Toki.
That's the one. The FFT is fundamental to virtually all modern digital signal processing. Everything from Wi-Fi and compression to medical imaging relies on it.
So Lemaître, in his pursuit of cosmic truths, accidentally laid groundwork for the digital revolution. He was simultaneously solving the problem of the universe's origin and the problem of efficient calculation.
His intellectual breadth was just staggering. We also see his mark on pure mathematical physics with the Lemaître-Tolman metric, which is an inhomogeneous solution of Einstein's field equations that describes a spherical dust cloud. It's a key tool in understanding density variations in the early universe. He worked in the three-body problem. He wrote an essay on quaternions. He was a polymath who never confined himself to a single subdiscipline.
For many of us, I think the most enduring puzzle of Georges Lemaître is how he balanced these two enormous callings, the priesthood and the pursuit of purely physical laws.
And this brings us to his crucial philosophical distinction, his rejection of what is known as concordism.
This section is vital for you, the learner, especially in today's world where conflicts between worldviews often dominate. So what is concordism exactly?
Concordism is the intellectual effort to force religious texts, like the Book of Genesis, into direct agreement with contemporary scientific knowledge. It's the attempt to show that the Bible is, in fact, a hidden science textbook.
And the sources reveal Lemaître actually played with this idea early on, didn't he?
He did. In 1917, while he was on leave from the military, he wrote an essay attempting to prove the classical philosophical notion of ex nihilo nihil fit out of nothing, nothing comes.
How did he try to do that?
He did it by arguing that because all matter emits light, absolute darkness would necessarily imply nothingness before the biblical fiat lux, let there be light. He was using basic physics principles to try and validate Genesis.
But he abandoned that path decisively. What was the mature Lemaître's final, firm view on the relationship between his faith and his science?
He emphatically rejected concordism. Lemaître argued that his work as a scientist should be judged on purely scientific criteria derived from observation, mathematics, and testable hypotheses.
And he worried that linking his expanding universe theory to a theological idea would have negative consequences.
Two very negative outcomes, he thought. First, he felt it would trivialize faith by trying to prove the infinite through the finite tools of science. And second, and critically, he feared it would hinder the scientific acceptance of his theories if they were perceived as thinly veiled theological arguments intended to prove creation.
He demanded that his scientific work stand or fall on its own merits.
And he stated the separation so elegantly. His famous quote, often cited, is deeply clarifying. Once you realize that the Bible does not purport to be a textbook of science, the old controversy between religion and science vanishes.
He then stated it unequivocally.
There is no conflict between religion and science to reconcile. For Lemaître, faith addressed the why and the spiritual condition, while science addressed the how and the physical condition. They occupied separate, non-overlapping domains.
This firm boundary was put to the ultimate test in 1951. It resulted in a fascinating piece of institutional drama. By this point, Lemaître was a highly respected cleric and was serving as the president of the Pontifical Academy of Sciences.
In 1951, Pope Pius XII gave a formal address to the Academy. The Pope, who was thrilled with the Big Bang concept, explicitly drew a parallel between Lemaître's primordial singularity, the fiat lux, and the Christian doctrine of creation.A.
Creation out of nothing.
Exactly. The Pope suggested that modern science had confirmed the creation event described in Genesis.
That sounds like a powerful public endorsement that would have made Lemaître's theory instantly acceptable to billions of Catholics, yet Lemaître was reportedly horrified by this.
He was horrified because it was the exact kind of concordism he fought against. He recognized the profound danger.
What was the danger?
If science, which is constantly evolving and self-correcting, was tied to a theological truth, what happens if the science changes? If the Big Bang Theory were ever superseded, it would undermine the credibility of the religious doctrine that had endorsed it.
So Lemaître, the humble priest-physicist, had to correct the highest religious authority. That takes immense courage and profound conviction.
It does. Lemaître, working with the director of the Vatican Observatory, Father Daniel O'Connell, successfully convinced the Pope to step back. They argued passionately that the Church must not attach eternal theological significance to a provisional physical theory.
And the Pope listened.
The Pope agreed and refrained from making any further public statements on religious or philosophical interpretations of physical cosmology.
That is a remarkable achievement. He successfully defended the integrity of both science and faith from the well-meaning intervention of the Pope himself.
It defines his legacy outside of physics. He was the intellectual architect of the non-overlapping magisteria, long before that phrase became common. He proved that one could hold deep faith and apply the most rigorous scientific methods without compromise.
And finally, a small note about another Nobel laureate, Paul Dirac, who shared an interesting observation with Lemaître.
Dirac suggested to Lemaître that cosmology, because it deals with the origin and ultimate fate of the universe, the grandest questions, was the branch of science closest to religion.
And Lemaître disagreed.
He politely disagreed. After consideration, he suggested instead that psychology, dealing with the inner life, the human condition, and morality, was actually closer to the realm of religion. This choice just reinforces his commitment to keeping faith focused on the spiritual and human experience, entirely distinct from the physical laws governing the universe. Hashtag tag outro.
So we have completed this deep dive into the life of Georges Lemaître, the decorated World War I veteran who challenged the greatest physicists of his time, the priest who refused to let his faith validate his science,
The theoretical genius who proposed the ultimate origin story of the cosmos, the primeval atom. He pioneered computational physics, he championed the cosmological constant, and established a crucial lasting boundary between scientific methodology and theological truth.
His final triumph came at the most poignant moment. Lemaître died shortly after hearing the news of the discovery of the cosmic microwave background radiation in 1965.
That faint, residual warmth, that scientific validation of his expansion theory, provided the definitive experimental proof of his hypothesis. A moment of extraordinary closure, almost 35 years after he first published the idea in Nature.
His legacy is indelible. His name is etched into the very framework of our understanding of the cosmos. The lunar crater Lemaître, the Friedmann-Lemaître-Robertson-Walker metric, the basic mathematical model for a homogeneous expanding universe.
And of course, the formal adoption of the Hubble-Lemaître law in 2018. His ideas now literally define our physical geography and the history of everything.
For our final provocative thought for you, the learner, let's return to that question of expertise. Late in his life, Lemaître was asked to serve on the Pontifical Commission on Birth Control.
He ultimately declined due to poor health, but he confided in a colleague, expressing concern that he thought it was dangerous for a mathematician to venture outside of his area of expertise.
Considering this was a man whose genius spanned everything from the structure of the smallest quantum to the largest scales of the accelerating universe, who understood the boundary between faith and science better than anyone, where do you draw the line between informed speculation and venturing outside one's professional expertise?
It's a question Lemaître, the ultimate intellectual boundary crosser, still forces us to confront today. Thank you for joining us for this deep dive into the extraordinary life and expanding universe of Georges Lemaître.